So yeah, my name is Gonzalo. I'm a GPU architect at NVIDIA. In my day job, I design GPU concurrency features. They span from our hardware ASAs to the user-facing programming models in languages like C++, and everything in between like LLVM. Some of these features make their way into the C++ standard, the study group for concurrency and parallelism, SE1. And there we review features like senders and receivers, parallel synchronization primitives like atomics, logs, barriers. In a past life, I was a computational scientist working on fluid dynamics, and today's talk intersects all of these topics. So, a few decades ago, Phil Colella, who is sort of a geology legend, identified that at the time, most of the scientific workloads that were running on HPC built on top of 7 main classes of algorithms. And furthermore, identified that these algorithms were actually quite well suited to the abstracted by library APIs. So for the past decade, we have been evolving the C++ standard library with many parallel algorithms. And I think it's fair to ask how well suited are current C++ standard library APIs for these problems, and is there something that we're missing? So just to give you an overview, these are the main 7 classes of algorithms that we identified: solving physical problems in structure and structured grids, irregular problems involving particles like embodied simulations, dense and sparse linear algebra like matrix multiplies, fast Fourier transforms, and Monte Carlo methods. I go to quite a few HPC conferences, and every conference I visit always has a few papers showing how to accelerate structure and structured grid problems with C++ parallel algorithms. These mainly use parallel for and parallel reduce. I've seen there are a few papers on Monte Carlo simulators. C++26 added standard linear algebra, which is an interface to BLAS. So if you have a dense linear algebra problem, you're good. We don't have any portable interfaces for sparse linear algebra. That's kind of a hot topic right now, and we don't have any portable interfaces for fast Fourier transforms. Maybe we should. So the one topic I actually hadn't had any talk on or any paper on was irregular particle-based simulations with portable C++, in particular involving tree-like data structures like an object like that. And that's actually what I'm going to talk about today. So this is what we're going to do. First, we're going to recap the basics of the C++ parallel algorithms. Then we are going to apply them with a few C++ 20 and C++ 23 features to parallelize embodied simulations. And we're going to be doing that in 3 different ways, and you will see later why. And finally, I'm going to just give you a sneak peek of what's coming in the parallelism space in C++. So, the parallel algorithms, let's start with some context. So, most modern hardware is highly parallel. Like, all the hardware in front of me, my laptop, my phone, has a multi-core CPU in it, has a GPU in it, and has many other accelerators in it. So, unfortunately, most of the C++ programs I see are kind of completely sequential, and that means that they are limited to using a small fraction of this hardware. The committee back then identified the root cause as the barrier of entry for parallel programming just being too high, and the C++ parallel algorithms is just an effort to change this. So, to provide batteries included on ramps in the standard library for writing parallel code, with the main goal of achieving widespread adoption of parallelism throughout the entire C++ ecosystem. So, the parallel algorithms are universally available. They come with every C++ implementation. They enable hardware vendors to provide optimized implementations for the hardware. For example, if you have a Linux NVIDIA system, the standard library can actually accelerate your parallel algorithms on GPUs. And while we don't aim to expose every single capability of every individual platform, the parallel algorithms interoperate with platform-specific extensions that allow you to do so. So you can actually mix C++ parallel algorithms with extensions like OpenMP, OpenCC, CUDA, CCL, and so on. So let's walk through an example. So here we have 2 contiguous sequences, x and y, and a scalar s. And we have a sequential loop that scales every element of x with s, and then adds its result to the corresponding element of y. The parallel algorithm version is how it looks like. So it's using the new C++26 parallel range algorithms, which were adopted into the working graph today. It's using the new indices view, which makes the algorithm much easier to use. This was also included into the working graph today. And now, instead of a sequential for loop, we have a call to the for each algorithm with a parallel execution policy as its first argument. So all parallel algorithms accept an execution policy as the first argument. And this policy describes how the algorithm may be parallelized. We'll learn more about this later. In this case, Parallelism describes that the algorithm may be safely parallelized and vectorized. Now we pass a range from 0 to size -1 using the indices view. And before our loop body was just in the loop, now our loop body is passed as a lambda. So this is a single version of our program. It's as portable as the raw loop we had before. And we can now compile this onto a bunch of parallel hardware. The end application is typically the one that controls where the parallel algorithms run, like the standard with the parallel algorithms doesn't currently provide a facility for this. It's something that's changing in the future. Which compiler flag to use is compiler dependent, like std for standard parallelism is available in multiple compilers, and it allows selecting between, for example, whether you want the parallelisms to run on multi-core CPUs or on a GPU. Right now, there is a wide range of implementations available from different communities like DCC and Clang, and also properly supported by multiple vendors. So we have implementations from AMD, Intel, and NVIDIA that support offloading the parallelisms to all of the GPUs. There is a small caveat here, which is that if you want to offload the parallel execution policy on GPUs right now, there are only two implementations that do this, and this is the TCP and the NVIDIA implementation and only on NVIDIA GPUs. But all of them they still run in parallel on the CPU. And this is the performance that you get on a wide range of systems from the example we saw before. So the y-axis shows how efficiently does our C++ program utilize a system that's shown on the x-axis. So the y-axis shows the program performance with respect to the hardware's theoretical peak. 100% is unattainable in practice. And the x-axis contains CPUs and GPUs from AMD, Intel, NVIDIA, and two other ARM CPUs from Amazon and Ampere. So overall, the program achieves at least 60% perf, but on many systems of the CPU, the number is much higher. So for example, on the GPU systems, it's closer to 90%, which means the largest theoretically possible improvement you could get from moving to a different programming model that's not portable outside C++ would be less than 10%, so maybe not worth it for this type of code. The main three key ingredients that we need to understand to write parallel C++ code are first the parallel algorithms, there are many of them, then the ranges to use them effectively, and finally the execution policies. So the parallel algorithm APIs are mostly identical to the sequential ones, so if you have ever used standard for each, I really don't have to tell you much about it. The main difference is that they accept an execution policy as the first argument. So there are many parallel algorithms in the standard, but the top 5 groups that I tend to use often are the iteration ones, like for each, reductions like transform, reduce, and reduce. Some of them are in the numerics header. Algorithms for data movement, like fill and copy. Parallel scans, like exclusive scan, inclusive scan, there are many problems you can solve with those. And other, like sort, unique, find, so we have parallel versions of those. This is, for example, how the transform reduce looks like. There are many overloads, this is just one of them. The first argument is execution policy, the second argument is a range. We have an initial value, in this case 10. Then we accept a reduction and a transform operator. So in this example, we scale every element of the input by 2, and then we add all elements together and return the result. The other set of concepts you have to be familiar with are range and use. So C++ has two concepts, two integrated concepts for abstracting iteration over sequences of elements. Sequences that can be iterated on using the range for loop, and the ranges. Views are a kind of range that is cheap to copy, whereby cheap would typically mean constant time complexity to copy. So a vector is a range we can iterate with a range for loop, but it's expensive to copy. Copying a vector is linear complexity, we have to copy the n elements, so a vector is a range, but it's not a view. The standard indices view we saw before, it describes a sequence from 0 to n-1. It's a range, it can be iterated exactly the same way, but in contrast to a vector, indices view only stores a pair of integers, so it's very cheap to copy, it's constant time. So standard like view indices is both a range and a view. In scientific computing, there are many problems that require iterating over multidimensional data. C++23 added a new view called Cartesian product that's really helpful when doing that. So Cartesian product returns, it takes a number of ranges as inputs, and it returns a one-dimensional range as output with a tuple element type. So to iterate over a two-dimensional data, we can just create one view of indices per dimension, then we can build a Cartesian product view that picks the first element of the first view and combine with every element of the other view. And then it picks the second element of the first view, combined again with every element of the second view, and so on. So when we iterate over the view or element E in the range view, it's a tuple. So we can use structured bindings to extract our X and Y indices, and then we can use them to access multidimensional data, for example, on an span directly. And you can use this view with the parallel algorithms to perform multidimensional iteration if you have multiple nested loops. Another view that's really useful is the SIP view. So a common problem when writing parallel code is trying to sort a vector of values using some vector of keys. The C++23 SIP view ties multiple ranges together into a single range of tuples so that they can be operated in lockstep. So to sort both vectors in lockstep by key, we first SIP both vectors together, then we sort the SIP view itself using a comparator that first extracts each element, like the key, the key of each element using structured bindings, and then we perform the comparison only by looking at the key and not looking at the value. So we really talked about the execution policies. So the execution policies describe how parallel algorithms may be executed. So they allow implementation to assume something. They don't really prescribe what the implementation needs to do. Like running all of the parallel algorithms sequentially is a valid implementation strategy. The PAR, or parallel policy, basically states that it's safe to parallelize an algorithm across threads. It allows threads to synchronize. They can take critical section logs, and we'll see some examples of that later. The parallel and sequence execution policy also enables the implementation to assume that it's safe to vectorize iterations within a single thread. And it requires threads to progress independently from each other and prevents them from synchronizing. So you cannot take logs and do things like that when using parallel. Where algorithms execute is up to the implementation, everything goes single thread, CPU threadpool, GPU stream. Right now, control mostly the compiled flags. So in these sections, we'll apply these features to parallelize irregular embodied simulations. So we have prepared a demo. It simulates two colliding galaxies using all the strategies we're about to see. Some of the concurrent algorithms that we have developed for it are pretty hard. Everybody that works on these things, these algorithms are hard. So I'm going to focus on the main ideas, but all of this is on GitHub. We'll share a link at the end. So if you want to go into the coding details, you can just check out the GitHub repo and try them out. So this is a collaboration that we did with a few people from the University of Bristol, Thomas Castle and Todd Dicking, a few people from the University of Heidelberg, Axel Alte. He develops adaptive CPP, it's an open source implementation that can target all possible CPUs and GPUs using C++ parallelism. And Vincent, this work was accepted and presented at Supercomputing 2024. And there is a write-up that goes over everything I'm going to talk to you about in way more detail. So if you're interested in the details, you can also check it out. So first of all, like a very brief crash course on embodied problems. In an embodied problem, we have embodies moving up at a particular velocity, and they react to the gravitational force that each body impacts on each other. So to take the position of a body, we need to have things like the old position, velocity and acceleration, and the acceleration depends on the total gravitational force that acts on a single body. And this force at this one particle contains contributions from each other particle. The contributions are expressed as a sum, so for every particle we go on some contribution of every other particle, and these contributions are weighted by the inverse distance, so the farther away a particle is, the smaller this contribution becomes. So a simple implementation of this to update the particle positions looks kind of like this. We have a parallel for, each position can be updated independently from each other, and this is pretty much one-to-one the math we saw before. I'm just using a small 3D vector library to make it more readable. For the acceleration, we have another parallel for, using the balanced diffusion policy, And it goes over every particle and it accumulates the interaction with every other particle by having another sequential loop in it. So this algorithm is called, or we call it Albers, because it computes all force pairs precisely, and it's going to be our baseline. So by just using the para algorithms, we get a significant improvements from going from a single CPU core to multiple CPU cores. On this plot, we have systems on the x-axis, thus at the left of the line, and just using a single core. On the right, we have the exact same systems using multiple cores. And on average, across all the systems, when going from single core to multi-core, we get something like a 5 to 10x performance improvement, so like an order of magnitude in portable C++. The main advantage of the algorithm is we can run it on more systems than just CPUs, we can run it on GPUs. So here we have the plot where we have only the multi-core CPU results on the left and the GPU results on the right. I'm not just changing a compiler flag without changing your code. You can run this on CPUs and get another 5x throughput improvement for GPUs to CPUs of equivalent generations. So, as I said before, all pairs is going to be our baseline. It's super simple to implement, just 2 parallel force, but it has O(n) squared complexity. For every particle, we have to do n force computations. And this takes forever to run in the small simulation I showed you before. So to the point, like, it doesn't make sense waiting to the end. So how can we do better? The main idea of the algorithms that try to do better exploit the fact that force interaction of particles that are far away become very small. So we want to compute precisely force pairs that are close to each other and just approximate force pairs that are very far away. So the way we do it is we somehow find some set of particles that are close to each other, and those are going to get the all-pairs algorithm. And then we're going to be aggregating groups of particles, and instead of computing the force from one particle to all the particles in a group, if they are far enough away, we're just going to be computing the force approximated with some sort of virtual particle at the center of this group that approximates the contribution. And as groups get farther and farther away, we're going to be continuing this and doing hierarchical aggregation. And this means that we reduce the number of force pairs we have to compute from O(n) squares to n log n, which is much better. We have to do extra work to aggregate the particles, and it takes extra space to store the trees of these aggregations, but it's totally worth it. Like most of the time, like 99% of the time of all pairs is spent purely on the force computations, updating the velocity takes 0 time. So this sort of algorithm is called BANSAP, and it has a few steps. The last step is just updating the positions, it's the same for all algorithms. The first step, we need to compute some bounding box, then we need to build some sort of tree data structure, then we need to aggregate particles hierarchically, and finally we need to traverse this tree to compute the forces. So starting with the bounding box, what's the smallest bounding box containing all the particles? We want to find the minimum of x and y from each particle and the maximum of x and y from each particle and determine the corners of our bounding box. We can just use transform reduce algorithm, go over all the bodies and just map each particle to our positions to some unit box around the particle, and then our reduction performs an element-wise min-max to accumulate the minimum and maximum into a pair. So this is how we do a parallel reduction that ends up with the bounding box that we have here on the left. Building the tree is a bit more complicated, so now when we have our bounding box, we're going to use it as the root of a tree, and then we're going to be building the tree by inserting particles into the tree. So I'm going to focus here on a quad tree. In the demo we have both quad tree and opt tree. We have the root, we pick our first particle, we can just insert it. We're going to have the constraint that we want a box in the tree to contain at most one particle. So our bounding box is free, we insert our first particle, and we're done. Then we intend to insert our second particle, but we can't because our box is full. So we have to subdivide our box, for example, isotropically into 4 equally sized boxes, and then I'm going to be enumerating these boxes in this order, so 0, 1, 2, and 3 come first, and they form like a set shape. So after we have subdivided them, we can move 0 to its right position within the tree, and then we want to insert 1, but now 1 falls in the same box as where 0 currently is, so we have to subdivide it again, and we have to move 0 again to a different position, and finally we can insert 1. And we're going to be repeating this process. Now we can insert 2 in the box where 2 falls is 3. We can insert 3, we're going to insert 4, we need to subdivide again, move 3, and finally we can insert 4, and so on. Right, so this is quite straightforward to implement sequentially, but we want to build this in parallel, using a parallel algorithm, and that's where things get tricky. So one thing we're going to need is concurrent memory allocation. We want to be able to allocate new nodes, like we want to be able to insert bodies into the tree concurrently. So we're going to need to allocate memory for the nodes also in a concurrent way. So for concurrent memory allocation, we're going to do something that's very simple. We're going to allocate space for some fixed amount of nodes. So we're going to estimate how many nodes the tree is going to make. We're going to make an allocation once. And then we're just going to have an atomic counter, but it's going to tell us where is the first free node. And we're going to just be filling the tree in one iteration, and then in every iteration we just prune the entire tree, and in the next iteration we allocate it again. So we just need to insert this. So this is a very simple bump allocator. So we just have an atomic, and we want to allocate a node. We just do a fetch at the atomic, and the result of the fetch at is or set of n free nodes. When we're inserting particles concurrently into a tree, we're going to have to need an algorithm to prevent threads from racing against each other. So if two threads get to the same node and the node doesn't have any nodes allocated, how do you prevent all threads from trying to allocate memory for it? You want to just one thread to allocate memory for it and the others to wait. In this example here, we have a node that has a particle A in it, and we have 3 threads that are arriving at this node with particles B, C, and D. So they all want to insert in this tree. So one of the threads is going to win. We're going to have a concurrent exchange that's going to try to switch a free node from free to some locked state, and only one thread is going to win this concurrent exchange. The other threads are going to lose the concurrent exchange, and we're going to just make it wait to see the state change from locked to something else. The thread that won the concurrent exchange is going to allocate some memory using the fetch chart that we saw before. It's going to allocate memory in this case for 4 particles, and then it's going to move the particle that was in node to the correct position. After doing that, it's going to set the state of the node from lock to point to the position of the node it just allocated, and it's going to be using a release store to do that. And that release store is going to notify all threads that were waiting that the value has changed from lock to something else, so it's going to unlock every thread that was blocked on this. So now all threads are going to proceed, and they are just going to insert those particles independently. So this is the algorithm in a nutshell. It has a few more details, but this is the gist of it. There are a few properties about this algorithm that are important. If a thread locks a node, and while the node is locked, that thread is never scheduled again, the algorithm will deadlock. Like no other thread is going to be able to make progress. So this algorithm requires that when a thread locks a node, the scheduler eventually schedules the thread again so that it can allocate the nodes, set the particles, and block everyone else. This means that threads don't make progress independently from each other. So if we implement this with a parallel fork, using standard for each, we need to use the parallel execution policy. We're going to use something like parent seek, because parent seek requires every thread to be able to make progress independently from each other. Then, once we have our tree built, to aggregate the particles, we can do something simple. We can create a thread per tree node. If a thread starts in the middle of the tree, it just exits. If a thread starts on a leaf, it advances to its parent. Every parent has a counter. The last thread to arrive aggregates the contribution of all the children of the parent and just moves on. So nothing fancy here. For computing the forces, it's a little more complicated. We can do a stackless depth-first search. So for every body, we traverse the tree, and we want to compute the forces of that body with every body that's in the tree. When we traverse a leaf node, if it computes a body, we just do like a near accurate computation. If we are traversing a node and that node is not a leaf node, for example, node 2 might be a near node. If it's near, we go and traverse the children to try to compute the forces accurately. But if the node, like node 3, for example, is a far node, we just take the aggregated contribution that was at that node. And this is how we get our n log n computation. So going back to performance. So this is the same graph as we had before, like n log n, bits, n square, every day of the week. Albers is not really a great baseline. But we see that for the octree approach, actually the gap that we had before between single core and multi-core is now significantly higher. It's no longer 5 to 10x, it's more like 40x performance improvement. And when we look at multi-core CPU performance versus GPU, we have another 3-4x improvement there. But one of the things that we will notice is that you only get this improvement, in this case on the GPUs, because all the GPUs can run parallelism with the parallel execution policy. So we just can't use this octree algorithm on AMD or Intel GPUs yet. So this is a problem, right? Like the octree doesn't run on many GPUs. Sure, you can run those systems using the CPU. We are leaving a lot of performance on the table. Can we build something that's a little bit more portable that might run everywhere? And the answer is yes. We can pick a slightly different algorithm, but it's going to look very different. It's no longer like a textbook quadtree example. Instead, it's using something called an LBBH, like a linear bounding volume hierarchy. And it starts in the same space. We have a bounding box of particles, we have already computed it. And then the first thing we're going to do is we're going to try to we're going to grid all particles into a perfect Cartesian grid. We're going to assign each particle a cell of a grid. And then we're going to be trying to sort all particles along a 1D space filling curve. So a space filling curve is a curve that we're going to use to fill space. And we're going to be assigning an index of this curve to every cell in the grid. And that's what allows us to do a 1D mapping of all particles. So by sorting the particles along this curve, we're going to be ensuring that particles that are close to each other in space end up close to each other along the curve. Like that's the main goal of the curve. And the reason we need to do this now that I have sorted the particles is because we're going to be building a tree in a very different way. We're going to be building a tree bottom up. We're going to be computing bounding boxes of pair of particles. So here we have, for particles 0 and 1, 2 particles adjacent in this curve, we're going to be computing a bounding box. For the next 2 particles, 2 and 3, we're going to be building a bounding box. And one thing you can see already here is that bounding boxes in this tree overlap. This is something that in the tree wasn't possible, right? So we're going to be hierarchically creating bounding boxes until we only have one. And in contrast to the octree now, our data structure is a fully balanced binary tree. So it's very structured. The octree could be as irregular as the particles were, but this tree is always going to be perfectly balanced. As I said, it's built from the bottom to the top, instead of from the top to the bottom. And some of the bounding boxes overlap. The bounding boxes overlapping is a bit problematic because it means that sometimes you're going to be computing more forces than you needed. And that's going to be impacting performance a little bit. Like the algorithm, building these trees is 0% at runtime. The algorithm still spends most of its time computing force pairs. So the less of them you can compute, the better you will have. But now you have an algorithm that's written strictly in portable conforming C++. It runs on all multi-core CPUs and GPUs from all vendors, and it performs decently well. Like it's significantly better than our pair. It's O(n) again, and it's basically building on top of just parallel sort essentially. So being able to use something like a parallel sort algorithm, that's something that few programming models actually have. So with this, I wanted to wrap up. Like the main takeaways I have is that with the C++ 17 algorithms, we have many open source and vendor-specific implementations available running on both CPUs and GPUs. We have many new utilities in C++ 17, like ranges in C++ 20, parallel range algorithms now in C++ 26. We have many atomics improvements in C++ 20 as well. By combining all of this, you can actually parallelize very irregular problems very portably, both on CPUs and GPUs. And you can get a single version of your program that runs everywhere. You just recompile. In C++ 26, we have linear algebra as well. So if you have any sort of test problems, you can use that. And the linear algebra libraries, for example, on NVIDIA, that is patched to things like QBLAS, the GPU-specific BLAS library. We have the parallel range algorithms. We have new views like indices that make working with this much better. And one thing we did not manage to do for C++ 26 is asynchronous parallel algorithms. So all of the parallel algorithms in C++ 26 are synchronous. That means your CPU thread blocks until the algorithm completes. C++ 26 has senders and receivers. And one of the first things we're going to do for Super229 is provide a synchronous version of this so that you can build graphs of algorithms and just dispatch them, for example, to a GPU only once. If you want to learn more about this, there is a talk that goes into some of the details from CP.com 2018, Parallelism Concurrency for more GPU. It's a very similar strategy for building a trial. And if you're using parallel algorithms and you want to optimize applications that use them, I gave a talk at GTC 23 about common optimization strategies, how to analyze them, how to profile them on CPUs and GPUs, and the most common optimization strategies you can use to improve the performance of these workloads. Yeah, so that's all I have. The demo is on GitHub. The paper is linked there. It's a QR code if you want to check it out. Yeah, I'm happy to take any questions.